Imagine a river. It flows, it moves, and at its core, it's a substance, water, that is conserved. It doesn't just disappear, and new water isn't spontaneously created out of nowhere. This simple idea of conservation is the bedrock of many scientific principles, and in fluid mechanics, it's captured by something called the continuity equation. Let's simplify. Instead of a wide river, consider a pipe. Water flows into one end and out the other. We can talk about how much water is moving through the pipe per unit of time. This is what we call the flow rate. Now, what happens if this pipe changes its shape? If it narrows, the same amount of water that entered the wider section still needs to get through the narrower section. Since there's less space, the water has to move faster to keep up. It's like squeezing a hose, the water shoots out faster. To make this more rigorous, scientists use a technique called a control volume analysis. Imagine a tiny, fixed region in space, like a small imaginary box, through which the fluid is flowing. The fundamental principle is that mass is conserved. So, whatever mass of fluid enters this box must either leave the box or accumulate inside it. For steady flow, nothing accumulates. If our control volume is small enough, we can think about the mass flow rate going in and the mass flow rate going out. For the mass inside our control volume to remain constant, which is the case for steady flow, the rate at which mass enters must exactly equal the rate at which mass leaves. How do we quantify this mass flow rate? It depends on three things: the density of the fluid, how much mass is packed into a certain volume, the area of the face through which it's flowing, and the velocity of the fluid. So, mass flow rate is generally density times area times velocity. For outflow, we can think of it as a negative inflow. Now, let's get mathematical and consider a tiny, infinitesimal control volume, which we'll call dV. This little cube exists in a 3D space with coordinates x, y, and z. The fluid at this point has velocity components: u in the x direction, v in the y direction, and w in the z direction. This tiny cube has 6 faces. We need to consider the net flow of mass out of this infinitesimal volume. For the face perpendicular to the x-axis at x plus dx, the mass flow rate out is related to the velocity u at that point and the area of the face. Similarly, for the face at x, the mass flow rate contributes to the net outflow as a negative value. We do this for all 6 faces. Let's consider the faces perpendicular to the x-axis. The density is rho, and the velocity in the x direction is u. The area of each face is di times dz. The net mass flow rate out in the x direction is the difference, which simplifies to the partial derivative of rho u with respect to x times dx di dz. We apply the same logic to the faces perpendicular to the y-axis and the z-axis. The net outflow in the y direction involves v, and in the z direction, it involves w. The total net mass flow rate out of our infinitesimal control volume is the sum of these contributions. Now, according to the principle of mass conservation, the rate at which mass accumulates inside this tiny volume must be equal to the net rate at which mass flows out. The rate of mass accumulation is the change in density over time, partial rho partial t, multiplied by the volume dv. So, the rate of change of mass inside the volume, plus the net mass flow rate out, must equal 0. This gives us our differential form of the continuity equation. Since dV is a common factor in every term, we can divide the entire equation by dV. This leaves us with the most general form of the continuity equation for any fluid, compressible or incompressible, steady or unsteady. Notice the pattern of derivatives: d dx, d di, d dz. This is precisely what the divergence operator, del dot, represents when applied to a vector field. We can make this even more compact using vector notation. Let v be the velocity vector u, v, w. Then, the term rho v represents the density flux, essentially, how much mass is moving per unit area per unit time. The continuity equation then becomes the rate of change of density over time plus the divergence of the density flux equals 0. Now, a very common simplification in fluid mechanics is incompressible flow. For an incompressible fluid, the density, rho, does not change. It remains constant, no matter what happens. If density rho is constant, two things happen. First, the rate of change of density over time becomes zero because a constant doesn't change. Second, when we take the divergence of rho v, we can pull the constant rho out. So, the general equation simplifies dramatically to del dot v equals 0. This is the continuity equation for incompressible flow. Let's expand this incompressible form in our familiar Cartesian coordinates. Remember, v equals u, v, w the divergence, del dot v, is the sum of the partial derivatives of each component with respect to its corresponding coordinate. So, for incompressible flow, the continuity equation in Cartesian coordinates is the partial derivative of u with respect to x plus the partial derivative of v with respect to y plus the partial derivative of w with respect to z, all equals 0. What does this equation actually mean? Each term represents the rate of stretching or compressing in a particular direction. For example, partial u partial x is the rate at which the fluid element is stretching along the x-axis. For incompressible flow, the total change in volume, the volumetric strain rate, must be 0. The element can distort, stretch in one direction while shrinking in another, but its overall volume must be preserved. Let's look at a 2D example. For flow in the xy plane, the continuity equation becomes partial u partial x plus partial v partial y equals 0. This means the rate of stretching in the x direction must be exactly balanced by the rate of compression in the y direction. Consider a velocity field like u equals x and v equals negative y. If we plug this in, 1 minus 1 equals 0. So, this velocity field satisfies continuity for incompressible flow. This type of flow, where u increases with x and v decreases with y, is characteristic of flow expanding outwards from a point, like a source, or converging towards a point, like a sink. In 2D, the continuity equation ensures that no fluid is lost or created. Fluid flow isn't always in a simple box shape. Many problems involve cylindrical symmetry. In cylindrical coordinates r, theta, z, with velocity components ur, u theta, uz, the continuity equation for incompressible flow takes on this form. Notice the extra factor of r in the radial derivative term, which accounts for the increasing circumference as you move away from the central axis. And for flows with spherical symmetry, we use spherical coordinates r, theta, phi. The continuity equation here is even more complex, with factors involving r and sine theta to correctly account for how the area elements change with position. So, to recap, the continuity equation is fundamentally about mass conservation. It's a statement that mass cannot be created or destroyed. For incompressible flow, it simplifies to del dot v equals 0, meaning that the volume of fluid elements is conserved. This equation is absolutely essential. It's one of the core equations used alongside momentum conservation, like the Navier-Stokes equations, to describe and predict fluid motion. Whether you're designing an airplane wing, understanding weather patterns, or even analyzing blood flow in your body, the principle of continuity is always at play. It's a simple idea with profound implications, forming a cornerstone of our understanding of the dynamic world of fluids.